Hello everyone, in this video we will be learning about derivatives. So I will start with a brief overview about what derivatives are. So suppose I have this graph and in here I have a point A and I would like to find the slope exactly at point A. So I want to find the slope of the graph. So maybe it's something like this. I want to find the slope of this line, and this line is what we call the tangent. Now, what is the slope of this line? So let's try some techniques we might know. So first of all, the slope is the difference in y divided by the difference in x, which is y2 minus y1 divided by x2 minus x1. And the slope is also what we refer to as the rate of change. Now that we know this, maybe we can choose 2 points that are like close to A. So maybe a point here and a point here. And let's draw a line that passes between these two points. And this line is what we call the secant. And you will notice that this line might be similar, it might have a similar slope to that of the tangent, but it is not exactly. It is still different because, as you notice, they intersect here, so they are not parallel lines, they do not have the same slope. Now, how can we make them more similar? First of all, I will define 2 points, the points I used. So I will define this point to be A and this point to be X. And let's compute the slope the way we know how to compute it from high school. So it's f of x, which is the y value in here, minus f of a, which is the y value at point A, divided by the difference in the x values, so divided by x minus a. So this is the slope of the secant line. And now we want to make it closer to the slope of the tangent. How do we do that? We make x approach A. So we make x and A get closer to each other. Let's take two closer points. So I will erase the secant line we drew. So instead of taking points that are far, I will take points that are very close to A. So this is a secant with points that are even closer to A. We can see that the slope of the secant in this case is closer to the slope of the tangent. Because of that, this method in making x approach A works. So you might have noticed I'm using the words approach, get closer to, and this might have reminded you of our previous video about limits. If it did, then you are correct because we will be using a limit today. So, since we want x to approach A, we will take the limit, and then I will copy this slope that we used before. So the limit of f of x minus f of a divided by x minus a as x approaches A. This, in fact, is the definition of a derivative. Just for the sake of simplifying our lives, we will rewrite this definition in a different way. So we will let h equal to x minus a. And then we solve for x. So x equals to h, we move a to the other side, so x equals to h plus a. So the slope in this case becomes the limit. You see, we are just rewriting this previous function. So we have f of x. Instead of x, we write h plus a, and then we continue writing it the same way. Again, in the denominator, instead of x, we write h plus a minus a. And now we want x, we want x to approach a. And we said that x is h plus a, so we want h plus a to approach a. We can remove a from both sides, so we want h to approach 0. And in the denominator, we have h plus a minus a minus a cancel out, so we only are left with h. And this is our formula. Again, both of these are equivalent. They are just two ways of expressing the same thing, which is the definition of a derivative. In some cases, one of these formulas might be more practical. In other cases or other exercise, another formula might be more practical. So we will see that through practice. Now let's look at the formal definition of the derivative. The tangent line to the curve y equals to f of x at the point P with coordinates a and f of a is the line through P with the slope m equals to limit f of x minus f of a divided by x minus a as x approaches a, provided that this limit exists. So just wanted to point out that they used the point P up in our graph. We use the point A. It's the same thing, they just use a different point. So let's use the definitions, this definition, and let's use also maybe the other definition too. Any of them work. Let's use the definition of a derivative to find an equation of the tangent line to the parabola y equals to x squared at the point P with coordinates 1, 1. So let us begin. They told us P at the coordinates 1, 1. This is to tell us that we are finding it at x equals to 1. And this 1 is our a value. So a equals to 1. So let's start with the definition to find the slope. So the slope m equals to limit f of x minus f of a divided by x minus a as x approaches a. So we will continue every time we see a, we can replace a with 1. So we get limit as x approaches 1 of f of x minus f of 1 divided by x minus 1. So this is limit as x approaches 1. What is f of x? Our f of x is x squared. What is f of 1? They gave it to us. It is 1 divided by x minus 1. As usual with limits, it never hurts to plug in order to compute them. So if I plug in x equals to 1, I will get in the numerator 1 squared minus 1, which is 0, and in the denominator 1 minus 1, which also is 0. And this is a sign for me to either rationalize, either factor, either simplify in some sort of way. So in our case, we can factor the numerator. So this is a squared minus b squared. We can factor it to a minus b times a plus b. So x minus 1 times x plus 1. All of that divided by x minus 1. And now since I have x minus 1 in the numerator and in the denominator, I can cancel them out. And I'm left with limit of x plus 1 as x approaches 1 Again, let us plug in, and we get 1 plus 1, which is 2. So now we have found the slope of our tangent line. Now you don't have to do what I'm about to do now in a second, but I just want to use the other definition of the derivative. And I want to show you that both of them give the same answer. So let's try the other one. Limit of a plus a, limit of f of a plus h minus f of a divided by h as h approaches 0. So this is the limit. What is f of a plus h? So the function is f of x equals to x squared. So f of a plus h is a plus h all squared. Now what is f of a? It's a squared divided by h. And again, we know that a in our question, a is equal to 1. So instead of all of these a's, I can write 1. And now this leaves us with limit of 1 plus h all squared minus 1 squared divided by h. Let us expand this and then simplify this. So in the numerator, we get 1 squared plus 2h plus h squared minus 1 squared divided by h. Just if in case you would like to plug in to see what you get, if you plug in, you will get 1 plus 0 plus 0 minus 1 divided by 0. So this is in fact 0 over 0. And this is a sign that we have got to, we should simplify this in some way. So first of all, 1 squared minus 1 squared, we can cancel this out. Also, we have a lot of h's. We can factor the h in the numerator, and this will give us h times 2 plus h divided by h. And now we can cancel both h's from the numerator and the denominator, and this gives us the limit of 2 plus h as h approaches 0. And now let us plug in again. So if h is 0, we get 2 plus 0, which is 2. So this is just to show you that both of these give the same answer for the slope. Now that we have the slope, let us find the equation for the tangent line at the point P, 1, 1. So as you know, the equation for a line is y equals to mx plus b. And we know that the slope is 2. So we have y equals to 2x plus b. And we have a point 1, 1 that is on this tangent line. So we plug in 1 for the y value and 1 for the x value plus b. So this is 1 equals to 2 plus b. Let us solve for b. b equals to 1. We move the 2 to the other side. So 1 minus 2, which is equal to negative 1. So now that we have b, we can rewrite the equation of the tangent line as y equals to 2x minus 1. We will now learn about the instantaneous velocity of an object with position function f of t at time t equals to a. So this instantaneous velocity is, in fact, the derivative. It is the limit f of a plus h minus f of a divided by h as h approaches 0, provided that this limit exists. So now we can see we have two definitions of the derivative. The derivative is the tangent line to the curve y equals to f of x at the point P. It is the slope of this line, and it is also the instantaneous velocity of an object with position function f of t at time t equals to a. So we can see that the derivative has several ways in which it can be used. It is the slope of the tangent at a point, it is the instantaneous velocity at a certain time. So we will look at several of these definitions. Now, using this second definition that we used, let's look at an example. So example, suppose a ball is dropped from the upper observation deck of the CN Tower, which is 450 meters above the ground. What is the velocity of the ball after 5 seconds? So let's begin with this part A. So first of all, we will do this exercise and we will suppose that the position function s of t equals to 4.9 t squared is given. So using this position function, we would like to find the velocity when t equals to 5 seconds. And in this way, we would be finding the instantaneous velocity when t equals to 5 seconds. And going back to the definition we just saw, the instantaneous velocity at a point is the derivative. So let us find the instantaneous velocity at the point t equals to 5. So first of all, let's begin with the definition, which is limit of f of a plus h minus f of a divided by h as h approaches 0. Moving on, we will replace every a we see by 5 because a equals to 5 in this exercise. So f of 5 plus 5 plus h minus f of 5 divided by h. Moving on, we will compute what f of 5 plus h is. So f of 5 plus h, we look back at the function up here, which is s of t equals to 4.9 t squared, which tells us that f of 5 plus h is 4.9 times 5 plus h all squared. And f of 5 is 4.9 times 5 squared. All of this divided by h. Moving on, we will factor the 4.9 because both terms have 4.9 in them. So we will factor the 4.9, and this leaves us with the limit of 5 plus h squared minus 5 squared divided by h as h approaches 0. And as usual, it never hurts to plug in h equals to 0 to see what the limit might give us. So if we plug in h equals to 0, we get 5 plus 0 all squared minus 5 squared, which becomes 25 minus 25, which is 0 in the numerator. And in the denominator, we get 0. So this is 0 over 0, which is the sign that we have to simplify this fraction in some way. So maybe let's expand the numerator and then simplify it. So if we expand 5 plus h squared, this gives us 25 plus 10h minus h squared. And 5 squared, the last one here, it becomes 25. So as you can see, we have a 25 here minus 25. We can cancel this out, which leaves us with 10h minus h squared divided by h. And we have an h here, and an h in the denominator. We can factor the h. And this gives us h times 10 minus h over h. And we can cancel out the h's from the numerator and from the denominator, which leaves us with 4.9 limit of 10 minus h as h approaches 0. And again, since we simplified, let us plug in h equals to 0 to see what the limit might give us. So if I plug in 10 minus 0, this gives me 10, and this is the answer of my limit. So I should not forget the constant 4.9. So 4.9 times 10 is 49, and this is our answer. 49 meters per second is the instantaneous velocity of the ball after 5 seconds. This is part A. Now, let's look at part B. Part B asks, how fast is the ball traveling when it hits the ground? So, let's think about that for a second. If the ball hit the ground, then it actually moved 450 meters down. So, let's use this fact for part B. So now we know that it moved 450 meters. And we also know that the position at time t is equal to 4.9 t squared. So now we have that 4.9 t squared is equal to 450 meters because it moved 450 meters. So using this information, let us solve for t. So t is equal to 450 divided by 4.9, and we take the square root of this. And we would like to find the instantaneous velocity when t equals to square root of 450 divided by 4.9. So as usual, we would start with the definition of the derivative. So we would find limit of f of a plus h minus f of a divided by h as h approaches 0. So what we do is we can plug in everything in here. So our function is 4.9 t squared. So of course we can take the constant out, and we would be left with a plus h squared minus a squared. So now instead of a, let us plug in square root of 450 divided by 4.9. So we would get 4.9 limit of square root of 450 divided by 4.9 plus h all squared minus square root of 450 divided by 4.9 all squared divided by h, and the limit as h approaches 0. Now what we do to compute limits, as usual, we always try to start by plugging in h equals to 0. So if we plug in, we would get 0 over 0. So this is a sign that we should continue simplifying. So what we do, we simplify. So first of all, we can start by expanding and then simplifying. So we would get, for the first parentheses, we would get 450 divided by 4.9 plus 2h square root of 450 divided by 4.9 plus h squared. And from the second parentheses, we would get 450 divided by 4.9. What we can do is we can cancel the first and the last term because they are the same with opposite signs, and we are left with 2h square root of 450 divided by 4.9 plus h squared in the numerator. We notice that there is an h in both terms, so we can factor it out. So we get 4.9 limit of h in parentheses 2 square root of 450 divided by 4.9 plus h. All of this divided by h. We notice there is an h in the numerator and the denominator, so we can cross them out. We are left with 4.9 limit of 2 square root of 450 divided by 4.9 plus h as h approaches 0. Let us plug in to see what we get. We get 4.9 times 2 square root of 450 divided by 4.9 plus 0. And we write this on our calculator, and this gives us 94 meters per second.